In this video, we're going to learn about the intermediate value theorem. And to set the stage for this theorem, why don't we think about the following question. Suppose that we've got this function f of x that is a continuous function and that f of 2 equals 3 and f of 5 equals 9. And we want to know, is there a solution to the equation f of x equals 7? Why don't we go ahead and graph this function f, or at least what we know about it. First of all, we know that f of 2 equals 3, so that means there's a point 2, 3 on the graph. Let's draw that in. 2, 3. It's right here. We also know that f of 5 equals 9, so that's a point 5, 9 on the graph. So go over to 5 and up to 9 over here. Here's another point that is on the graph of f. 5, 9. Now we want to know, is there a solution to the equation f of x equals 7? Well, any solutions to the equation f of x equals 7 will occur where the graph of y equals f of x intersects the horizontal line y equals 7. So why don't we go ahead and draw this line here. Okay, so really we just want to know, does the function f of x have to cross this line y equals 7? Why don't we draw a couple examples for what the graph of f of x might look like? The simplest example might just be a straight line connecting these 2 points 2, 3, and 5, 9. So it just goes directly from 2, 3 up to 5, 9. And then, hey, there's a point of intersection right over here. Okay, so in the case of this simple kind of graph, there is a solution to the equation f of x equals 7. What if we draw a more complicated graph? What if it starts at 2, 3, and then goes down, and then goes up? It goes like little oscillation here, and then comes back down to 5, 9. Well, still, it crosses that line y equals 7, so there has to be a solution to the equation f of x equals 7. Alright, so it looks like the graph of f of x always crosses that line y equals 7. But let's think for a bit. Are we totally sure about this? Would you bet your life on it? Why don't we think about it a little bit longer? In particular, let's try to construct a function which doesn't intersect this line y equals 7. So in order to draw a function that doesn't cross y equals 7, but that goes from this point to that point, we would actually have to jump over that line y equals 7. We'd have to draw the function and then pick up our pen to jump over that line y equals 7. But we're not allowed to do that because we're told that f is a continuous function. That means it can be drawn without picking up one's pen. So our conclusion is that yes, there is a solution to the equation f of x equals 7. And that is because any graph of f of x must cross the line y equals 7. But there's actually even more that we can say. The graph of f of x must cross y equals 7 for some x in the interval from 2 to 5. At x equals 2, the function has to be below the line y equals 7, and at x equals 5, the function is above the line y equals 7. So somewhere in that interval, where x is between 2 and 5, our function has to cross that line y equals 7. So consequently, therefore, the solution to f of x equals 7 must be in that interval from 2 to 5. Now, one little nuance here, actually, there could be more than just this solution. So we should really just say, therefore, a solution to f of x equals 7 must be in the interval 2, 5. And to see that graphically, what I mean is there could be several times that our function f of x crosses that line y equals 7. Maybe after going down and coming back up and then going down, maybe it keeps going down and crosses that line y equals 7. And maybe it keeps on doing that. Maybe it has a ton of solutions. So we can't actually say anything about the number of solutions it has, but we can say that there is definitely some solution, at least one solution, there might be more than one, in that interval from 2 to 5. Alright, so this problem sets the stage for the intermediate value theorem, which we'll state right here. The intermediate value theorem states that let f of x be a function that is continuous on a closed interval a, b. So given this function that is continuous on a closed interval a, b, if k is a number that lies between f of a and f of b inclusive, then there exists a number c in that interval a, b, such that f of c is equal to k. Alright, so that's a lot of wording, a lot of symbols, so let's explain this in the context of this problem that we just did. So first of all, let f of x be a function that is continuous on a closed interval a, b. Well, in the problem, we suppose that f of x is a continuous function. So that means it's continuous everywhere, and in particular, it is continuous on this interval from 2 to 5. So in the problem that we just did, a was equal to 2, and b was equal to 5. So the function f was continuous on this interval. Now, the number k in this problem was the number 7. So this is k in the problem. Actually, why don't we write it by the axis for some added clarity? This is k. Now in this problem, k is a number that lies between f of a and f of b, because k is just 7, a was 2, so f of a, we're told that f of a, f of 2 is 3. So f of a is right over here. It's right at 3. And f of b is right over here at 9. So k is clearly between f of a and f of b, so we're told that there exists some number c in the interval a, b such that f of c equals k. So we're saying there's some number c in this interval here such that the output of the function at c is equal to k. So in particular, for this green function, one of the possibilities for f that we drew, c would be right below this intersection point. It would be that intersection point, the x-coordinate of that intersection point. So it would be right around over here. So that would be c, and then that intersection point right over here would have the y value of k. So k would be equal to f of c. For the possibility of the blue function, the simple function that we drew, the point of intersection is shifted over just a little bit, so in that case the point c would be shifted over to the right just a little bit. But either way, we are guaranteed an x value, c, in that interval from a to b, such that the function output at c is exactly equal to k, that value k. And that would be a solution to the equation f of x equals k, which in this case was 7. So that's the intermediate value theorem, and I highly recommend that you remember this theorem because it comes up all the time when we're studying continuous functions. And really what it says is if the graph of a continuous function hits any two y values, then it has to hit all those y values in between. Okay, next question. According to the intermediate value theorem, for which values of k does the equation x squared plus x equals k have a guaranteed solution on the interval 1, 3? Alright, so why don't we go ahead and try to fit this into the form of the intermediate value theorem. We'll take this equation x squared plus x equal k, and why don't we lump this expression here, x squared plus x, we'll lump that into a function g of x. So we'll say g of x is equal to x squared plus x. Why don't we draw a little graph here to help us visualize? So we want to find what values of k does the equation g of x equals k have a guaranteed solution on this interval 1, 3. Let's draw on that interval over here, 1, 3. So this is the interval where we're interested in solutions of the equation g of x equals k. So in terms of the intermediate value theorem, we have that a equals 1 and b equals 3. Let's also get the values of g of a. G of a is just equal to g of 1, because a is 1. So plugging that into our equation for g, we have that's 1 squared plus 1, which is equal to 1 plus 1, which is equal to 2. So g of a is 2. Let's draw that right over here. That's at 2, and that is g of a. Let's also do the same for g of b. G of b is equal to g of 3. And plugging that into our equation, that's 3 squared plus 3, so 9 plus 3, which is 12. So we can go ahead and plot that on the graph, g of 12 all the way up here. So there is 12, and 12 is g of b. Now remember what the intermediate value theorem says. The intermediate value theorem says that for any function that is continuous on some interval ab, first of all, we have our function here. On the interval ab, it is continuous because this is a polynomial, which means it is continuous. So we've got a function g of x that is continuous on this interval ab, and the intermediate value theorem says that for any value of k between g of a and g of b inclusive, so for any value of k between 2 and 12, let's just darken that in, for any value of k over here, k is anywhere inside of that interval, there is some value of c in this interval, the interval ab, somewhere inside of there, such that g of c is equal to k. Now that value c would be a solution to the equation x squared plus x equals k, because we would just have c squared plus c equals k, according to the definition of our function g. So really, we've got a guaranteed solution on this interval 1, 3 for any value of k between 2 and 12. So there's the answer to our question. We just need k to be in the interval from 2 to 12. Next question, on which of the intervals can the intermediate value theorem be applied to the function h of x equals x over x plus 2 times x minus 1? Well, think back to the assumptions of the intermediate value theorem. What has to be true about this function h and the intervals that we're talking about? Well, the intervals have to be closed, and the function h has to be continuous on those intervals. So let's sum that up by writing that we can apply the intermediate value theorem, IVT, to any closed interval on which h of x is continuous. Keywords there being any closed interval, and that h of x has to be continuous. Okay, so what are the closed intervals on which h of x is continuous? Why don't we just think about the intervals that don't work, the intervals on which h is not continuous? And to figure out those intervals, we need to figure out what are the discontinuities of h. So think, what inputs cause a problem in h? Well, h is a rational function just being a fraction, and a fraction has an issue whenever there's a 0 in the denominator. So whenever x gives us a 0 in this denominator will form a discontinuity of h of x. So why don't we just go ahead and set that denominator equal to 0 and solve for the result. So x plus 2 times x minus 1. At the discontinuities, this product will equal 0. So using the zero product property, if two factors multiplied together equals 0, then one of the factors has to be 0. So we have x plus 2 equals 0, or x minus 1 equals 0. And if x plus 2 equals 0, then x equals negative 2, whereas if x minus 1 equals 0, then x equals 1. So here we have the discontinuities. The discontinuities of h are x equals negative 2 and x equals 1. So now we can be a bit more specific about what we mean by any closed interval on which h of x is continuous. This is really any closed interval that does not contain x equals negative 2 nor x equals 1. So there we go. There is a perfect specification of what kind of intervals we can apply the intermediate value theorem to for h. But just to be very clear, why don't we give some examples? So some examples of valid intervals include the interval 5, 10 and the interval -7, -6. To verify that these are valid intervals, just ask yourself, given an interval, does it contain x equals negative 2 or x equals 1? Well, the numbers between 5 and 10, no, they don't contain negative 2 nor 1. Same with the numbers between -7 and -6. Neither negative 2 nor negative 1 is contained inside that interval. So both of these intervals are good. Now, what about intervals like 0, 10 or -7, -1? Just ask yourself the same question. Does the interval contain x equals negative 2 or x equals 1? Well, 0, 10 clearly contains 1. 1 is between 0 and 10. So this contains x equals 1. And h is discontinuous there, so no, this is a bad interval. And how about the interval -7, -1? Well, that one contains x equals negative 2. So that is also an invalid interval. So there we go. Now we know how to use and state the intermediate value theorem. We know about continuity, and in the future we'll also learn about another core concept of calculus, differentiation.